the goal is simple. Break these concepts down so that any who is determined with this basic knowledge will learn and proceed from there. This is the GMAT 41. You are welcome to our engineering mathematics class. Yes, when I pronounce engineering maths, do you then feel that this class is meant for the engineering students? Please, may that never be so. For the concept of course titles given is just to define a particular course. It also spread to other aspects of your learning. As a matter of fact, this is simply mathematics class. Think physics, think chemistry, think mathematics and the associated courses to these subjects. GMAT 41 always gets you covered. In this class, we are going to give attention to one part of trigonometry. I would like you to watch the screen and see this appear. This is known as the unit circle. Now, of course, taking a look at what you're seeing on the screen now, this circle might seem a bit complex. And someone will be like, wow, what is this? Maybe if you're just beginning your 100 level and you would be like, gosh, you've not started. Just imagine all these many things. But relax. Hey, these are very simple concepts. Now, if you look at this circle, what a circle is all about is simply to teach you the concept of how to obtain the values of the sine, the cos, and the tan of special angles. In trigonometry, there are angles we call special angles. In one of my previous video lessons, in a course titled Math 101, Elementary Mathematics, I had already discussed under a Gann diagram, complex number, the idea of maybe talking about the generation of special angles. I use the concept of 0, 30, 15, 15, 30 degrees generator. Once again, 0, but one can decide not to bother about the 0. You can kick off with your 30, 15, 15, 30 degrees generator. With these 4 angles, you can get all the special angles as have been established so far. So we're going to study these concepts and then further look at how we can use the knowledge to deal with angular conversion from one unit, say in degree, to another unit, say in radian, to another unit, say in minutes, in seconds, and of course in hours. You will love this class as always. To start with, I would like you to take a look at this right angle triangle. And this is 90 degrees. Let me assume that I have an angle fixed here. By the way, the angle can also be fixed here, it doesn't matter. But the angle can never be fixed here, for this is a special angle when dealing with our right angle triangle. In fact, this angle, which is 90 degrees, is what determines a triangle to be a what? A right angle triangle. That is like the identification mark. Now, these other 2 angles, any one of them can be given, alright? The choice is yours. With this, you're going to label these 3 sides of the right angle triangle. This side is the opposite, and I will tell you why. And we're going to use, say, Y to represent the opposite. Yeah. The opposite of a right angle triangle is simply the side facing the given angle. The side facing the given angle. Here the given angle is this theta. This 90 degrees is not the given angle. For I call it the follow-come angle, this 90 degrees, okay? So it is not given. It's a special character, an angle that comes with any triangle that is called a right angle triangle. The ones that I refer to as the given angle is either this or this. So the side facing the given angle is the opposite. Now look at this given angle in my diagram. If you trace it, draw a line from that angle there, you see it will touch this side of the right angle triangle. Therefore, this side faces this angle given, and we call it the opposite. Alright, now we are moving on. This side, which is, of course, the longest side, is the hypotenuse. And how do we actually identify the hypotenuse? We say the longest side, fine. But then another better explanation to it is the side facing the right angle. The side facing the right angle, facing the 90 degrees. Are you following, right? If you dot a line from this 90-degree angle, dot, 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 it will touch this side, the longest side. So this is our hypotenuse. I'm going to use Z to represent it. Then hypotenuse, let me say high. Okay? High. And of course, we are left to the third side where we have no other choice than label it as what? The adjacent. This is the adjacent. Adj. I'm going to use X to represent it. Now, you see something about the adjacent. The adjacent is the third side of the right angle triangle that does not face the given angle. The third side of the right angle triangle that does not face the given angle. That is our adjacent. Now, before we move on to this, please let me ask, what if I had given this side? Let's assume that this is our given angle. I fixed theta here, and there is no theta here. Are you following, right? Automatically, you'll agree with me that the opposite and the adjacent will switch. Because if here becomes the given angle, the side facing it will now be this horizontal, which we'll now call the opposite. Whereas this side will now become adjacent in that case. The hypotenuse remains unchanged. The side facing the 90 degrees. This is good. Now, with this right angle triangle, what we want to do now is to establish the basic trigonometric functions. Once again, the basic trigonometric function, the basic trig functions. Like when you are studying trigonometry, the starter points, all right? And that will take us to talk about the sine, the cosine, and the tangent of an angle. This is the first thing we want to give our attention to. So we're going to study what sine theta is, cos theta, and tan theta. This perhaps could be something like, this is quite too simple. Anyway, from JSS2, all right, yeah, from JSS2, JSS3, we get introduced to this concept. But hey, that shouldn't be your problem. You see, in learning process, to develop our knowledge into the unknown, as the case might be, you want to first analyze and understand basic knowledge. All right, it's from there now you blow out and expand the network of that brain in order to get much more deeper concepts. All right, so in as much as I am going to start by saying sine theta is opposite of a hypotenuse, cos theta is adjacent of a hypotenuse, tan theta is opposite of adjacent. If you already know that, please don't tune out of this class. Follow up, for we'll have something wonderful coming. Besides, in our next class, I am going to be dealing with another concept of trigonometric identity, which will take its roots from this guy. So even though this is not really what we are focusing here, please, I am starting from here and I implore you to follow up. It's for your good. Whether or not you already have this knowledge. And for those who somehow they are having challenges with this before, you can use this class as a means of bolstering yourself up. Let's go. The first we are going to look at is sine. But before I do that, I'd like to say this. This is one concept in the study of basic trigonometry that we usually always remind ourselves of. So, ka, toa. Good. And what is the meaning of this so, ka, toa? S is sine. O is opposite. H is hypotenuse. C is cos, cosine. A is adjacent. H still maintains hypotenuse. T is tangent, tan. O maintains opposite. A adjacent. So the idea is this: if I want to obtain the value of sine theta, sine of an angle, it's simply going to be opposite over hypotenuse. So we're going to go back to our diagram and then ask ourselves, what is the opposite? The opposite here is y. So this is going to be y divided by hypotenuse, which is z, as I represented it. You may choose to use ABC. You can use any other alphabet to represent these three sides of the right angle triangle. It concerns nobody. Cos theta, that is cosine of an angle, is adjacent over hypotenuse. Our adjacent here is x. Hypotenuse still remains z. We're going to take this to be trig identity number 2. And then, of course, our tangent of an angle tan theta is opposite over adjacent. So for our diagram, what is the opposite? Y, adjacent, x. So this becomes y over x. I'm going to call this trig identity number 3. This is cool. So you don't joke with these three basic trig identities. It's from here we generate many other things when studying trigonometry. Am I communicating? Always remember, if you've got any question, please, this platform has, below this video lesson, created a comment box where you can drop your questions. If you have anything to contribute also, feel free to contribute. For the goal is simple, like I said, break down this concept, make it basic, no matter how it is, so that people, scholars, will learn, and from there, proceed. We are moving on to the next part of this discussion. Now, in this class, we want to establish the relationship between sine, cos, and tan. Let us see something, because I look at this identity number 1 and identity number 2, then thinking of the knowledge of division of fraction, I observe that if I do y over z divided by x over z, it seems like it's going to give me y over x. Alright? We can actually verify that. Let's see. So what I want to do is to take the ratio sine theta over cos theta. Let's see how it goes. I'm going to write here. Now, if I evaluate sine theta divided by cos theta, let's see what it's going to give to us. Now, sine theta over cos theta is going to give us, sine theta first is y over z. And then we are dividing it by cos theta, and cos theta is x over z. Now, the knowledge of division of fraction tells us that in a case like this, we have to keep the numerator exactly the way it is, which is y over z, inverse the denominator ratio. But to do that, this major division sign, change it to what? Multiplication. And then we inverse the denominator. So it's going to be z over x. This. See, I turned that denominator upside down. And clearly you agree with me that this z and z will cancel out. And once that happens, therefore, you could say that sine theta divided by cos theta gives us y over x. Now let us come back to identity number 3. Y over x is equivalent to what? That trig identity called tangent. So we conclude that tan theta, anytime you're evaluating tan of anything, it's also the same as taking the ratio sine theta over cos theta. And that, of course, is equal to the opposite over what? The adjacent, because y there is opposite, and then our x, is the adjacent. Alright guys, we are going to call this identity number 4. And this is quite interesting. Now, we can evaluate sine of a special angle, tan of a special angle, and cos of a special angle. Once again, you look at the screen as the unit circle displays. And then you're seeing that you see so many things written there. You see some things with pi, you see some stuff with, radical symbol, square root, as the case might be. Then of course you see angles there, 30 degrees, you see 45 degrees, you see 60 degrees, you see 90. In the first quadrant, moving on to the second quadrant, you have 120 degrees. If you add 15 to 120, you're getting 135. Add 15 again, I'm in the second quadrant now. Add 15 again to 135, you get 150 degrees. Now add 30 to 150 degrees, it will land you on the next side of the horizontal, which is 180 degrees. You can continue in that way to be adding 30, 15, 15, 30. Once again, 30 first, 15, 15 again, and then 30. You will generate all the special angles. That's just the secret of what is there in the diagram. And then to get the values of all those things you have there, square root of these, are you following? Pi over that. You just need to use these identities. Does that make sense? For example, locate 30 degrees, let's see. Locate 30 degrees in that unit circle, locate it. But in handling angular conversion, suppose maybe in your lecture you see reference made to this circle, what should you know about it? Now, 30 degrees there, you see, on the horizontal where you have 0, you move, you see the first line, 30, represents 30 degrees, measured anti-clockwise. Anti-clockwise, that is counterclockwise from the horizontal axis. And then you see that we've got, that 30 degrees, and there are values written there. For example, you see that value with pi there, pi over 6. By the way, that value, pi over 6, is the value of 30 degrees in the unit of radian. 30 degrees. degree as unit of angle, and then you have pi over 6. That pi over 6 is the equivalent of 30 degrees, but now in the angular unit of radian. And then when you move on, you see just outside, you see in brackets, value is given. Okay, I'm going to tell you the first one is the value of cos 30, and the second is the value of sine 30. Now, in this unit circle, we didn't bother to show the value of tan of those special angles. The reason is because once you know the value of sine and cos, you can get tan using the tan identity for sine over cos. All right, that ratio identity number 4. So with cos and tan, we are just okay. And what is the value of cos 30, as you can see there? All right, you know, cos is opposite over what? Cos is adjacent over hypotenuse. And of course, if cos is adjacent over hypotenuse, then of course we expect there's a triangle I'm going to show you soon, don't worry. But just based on that value we have there, cos 30 degrees, you now have it as root 3 over 2, root 3 over 2. That's going to be cos 30 degrees, right? Square root of 3 over 2. And then you now have sine 30. Sine 30 is 1 over 2. That is why in that line of 30 degrees, just outside, you have square root of 3 over 2, and then comma, you have 1 over 2. You can move on also to the next line. Let me quickly analyze that one of 60 degrees. You have that of 60 degrees, so you can evaluate 60 degrees to radian. And what you do to that radian is simple. Just multiply that 60 by pi over 180. Then if you solve that out, you're going to get pi over 3 in radian, which is what is seen there, pi over 3 radian. That's the equivalent of 60 degrees. Angular measurement in degree converted to radian, you have that pi over 3 as an equivalent in radian. Now, what about getting the value of cos 60 and sine 60? Evaluating cos 60, of course, cos 60 there, you're going to get our 1 over 2, as you see in that unit circle showing there. So that's why you have in bracket 1 over 2, then comma, right? What about sine 60? What about sine 60 degrees? Sine 60 degree actually is root 3 over 2. Sine 60 is root what? 3 over 2. And of course, one can still continue. If you work on 45 degrees, see the values there. I'll quickly also tell you how we obtain that. Please watch that 45 degrees. In 45 degrees, converting that 45 degrees to radian, what do we get? Just multiply the 45 by pi over 180. If you work it out, you get a value as expected, which is why you get pi over 4 as the value of the equivalent, pi over 4 radian, as being equal to the value 45 degrees then. Now, what about the cos and tan value of 45 degrees as a special angle? You can see there the values written. Now, cos 45 is actually 1 over square root of 2. 1 over square root of 2. Then you have comma, sine 45 is also 1 over square root of 2. But if you look at this unit circle, the values you have there, you know, it's not over square root of 2. So how did we actually get that value as you're saying there? If you have 1 over square root of 2, comma 1 over square root of 2, you can do what we call rationalization. Don't worry, in our classes, you're going to learn more under surd. You will learn about surd rationalization. Of course, in our channel here, under playlist of Math 101, you have that. And of course, for jump maths also, you have that. Video lesson covering that. So if I have 1 over square root of 2, I can multiply numerator by that square root of 2, multiply denominator by square root of 2. If you do that, you are going to get square root of 2 all over 2. Because in the numerator, you have 1. 1 times square root of 2 gives you square root of 2. Then all over, that denominator is square root of 2. If you multiply square root of 2 by square root of 2, it's going to give you square root of 4. And 4 is the perfect square, which will now give you 2. And that's how we actually got that 45 degrees, the sine and the cos of it, cos first as given there, and then sine, is actually root 2, square root of 2 over 2. Then comma again, square root of 2 over 2. So sine 45 and cos 45, they are equal. Does that make sense, right? If you move on to the other quadrant, you'll be seeing some bearing minus and other things. Of course, that is based on the fact that depending on the quadrant you're operating on, alright, I've dealt with that before in previous class. You can as well click this info link to take a lesson where I made mention of all these concepts. Are you following, right? Of sine will be positive in this quadrant. In the second quadrant, sine is positive. In the first quadrant anyway, all of them, sine, cos, and tan are positive. In the second quadrant, only sine is positive. You turn again, anti-clockwise. In the third quadrant, only tan is positive. It means that sine and cos they are negative, all right? If you move on to the fourth quadrant, only cos is positive. It means that sine and tan they are negative in that quadrant. So that is why in some of them you see minus there. All right, let's get back to our analysis on the board. We've established all this, and you can see how important this basic knowledge is. Looking at that unit circle, you've gotten at least a partial idea, if not all the idea. I guess the only thing that will hold you back now is just having your knowledge of basic arithmetics, this over that, get all those values of special angles from the angles we use for them. I'm going to draw the two triangles we use for that analysis. So you get to know how I actually even got to know all this idea of, tan 45, sine 45, cos 45, and the rest of them. Sine 30, cos 30, sine 60, cos 60. In the same way, if we move on to the second quadrant where 120 is found, 135 is found, and 150 is found. Alright, 180 serves as a boundary between second and third quadrant. And then we move on to the third quadrant where you have 210 degrees. If you add 15 to 210 degrees, you know what you get there, right? 225, as the case might be. And then you keep doing that 30, 15, 15, 30 addition. With the knowledge of this sine, cos, and tan, and then what I'm about to show you on the board, can actually get these whole values shown on that unit circle. These are the two triangles you need to be able to complete the whole work on that unit circle. Alright, so we have the perpendicular height. This triangle, by the way, is equilateral triangle. So actually, we have two units here. We have 2 units here. Then we have 2 units here. But you notice that this perpendicular, the height, divided this base into 2 parts. So here you have 1. That 1 is the value from here to the middle. Right, you have 1 there. And then from here to this side also, we give it 1. So that 1 plus 1 is equal to what? 2. And then this is angle 60 degrees. This is angle 30 degrees. Remember I told you it's equilateral. And because it's equilateral, this whole angle is 60, this is 60, this is 60. So since this angle is divided by 2, this will be 30. Of course, this will also be what? 30. In our analysis, you can just use any one of the right angle triangle here. 30 degrees. Here is 60 degrees. This is right angle triangle because for equilateral triangle, the perpendicular height, alright, meets one of the side at 90 degrees. Alright, so the second triangle, you need to also bear in mind, this is our right angle triangle. Now, this right angle triangle, this angle specifically is 45 degrees. 45 degrees. Alright. Then we have this value to be 1. 1, this is the 1. So the opposite and the adjacent are both 1, 1. Square root of 2. So these are the triangles we use to obtain all these values written just outside that circle. For example, I told you that cos 30 is root 3 over 2 and sine 30 is 1 over 2. How did I get that? If you use your Pythagoras theorem to solve for these perpendicular heights, these heights, are you following, right? Let's assume you pull out this right angle triangle and decide to obtain the value of this height. What you are going to get is square root of 3. Square root of what? 3. Please take note of that. You can work it on your own. So I want to get the value of maybe sine 30 and cos 30, sine 60, cos 60. What would I do? Simply come over. You have cos 30. You're going to focus on just one part of this whole triangle, which is one of this right angle triangle. Either you use this or you use this. The choice is yours. Cos 30, cos is adjacent over what? Hypotenuse, you know that. So if this is 30, here is the opposite because this side is facing this 30 degrees. The adjacent will be root 3. So cos 30 will be root 3 over the hypotenuse, which is 2. Root 3 over 2. And then sine 30, which is opposite over hypotenuse. This is 30, the opposite is 1. Hypotenuse is 2. So sine 30 is going to be 1 over 2, which agrees with what you saw in that unit circle for cos 30 and sine 30. Are you following, right? Now, talking about that of sine 60 and cos 60, for example, for cos 60, you locate 60 degrees, cos 60. With this 60 degrees, this perpendicular height becomes the opposite, automatically leaving us with this base as what? The adjacent. And of course, we have our hypotenuse as usual. So cos 60 will be adjacent 1 over hypotenuse 2. So you see that cos 60 is equivalent to sine 30 because both of them is 1 over 2. Are you following? Anyway, you can work out all of those things with this basic knowledge and concepts I'm giving to you already. Let's move on to sine 60. Sine 60 will now be opposite of hypotenuse as usual based on what we established. Now the opposite of this 60 degrees is this perpendicular height because it's facing it. So sine 60 is going to be root 3 over the hypotenuse 2. Root 3 over 2, which of course you see is the same as cos 30. Sine 60 is equal to what? Cos 30. Is that okay? Like I said, you can develop the rest of them using this triangle, and then you check that unit circle and see how those values actually came about. Let me quickly analyze that one of 45. You remember that one of 45 when I showed you that unit circle? We said that the value is root 2 over 2, both for cos 45 and sine 45. Both of them had the same value. Why? If you're evaluating cos 45, you're using this triangle. This right angle triangle is used specifically for 45 degrees. Now cos 45, adjacent over hypotenuse. This is the adjacent. Are you following, right? So it's going to be 1 over root 2. Sine 45 is also opposite over hypotenuse. The opposite is this, which is still 1 over hypotenuse, which is root 2. And I told you when I showed you that unit circle that by rationalization, if you have 1 over root 2, multiply the numerator and denominator by that root 2, we call it the conjugate of the denominator, you are going to actually get root 2 over 2, which of course, cos 45 and sine 45, they are equal, root 2 over 2, or simply 1 over root 2 if you don't want to rationalize. So that is how we actually came about those values, and I hope you enjoyed this concept. If you already know about it, fine. This is an added knowledge. Perhaps it's one thing you may have added from this video lesson to your knowledge. If this is your first time of learning this, it's a challenge you are picking in order to put an end to maybe anything disturbing you in this aspect of trigonometry before now. And the truth is, you need this very, very much. You need it in your various studies, especially in aspects of calculations where you might not have calculator that make use of all these trig functions, okay? An examiner in such case will give you questions on special angles where you can use this knowledge to evaluate them without calculator. A good example is the aspect of JAMB exam, for example. What about certain schools that take CBT in some of their exam, maths, physics, where you might need this concept? Like in physics, if you're studying vectors, there are areas you would need to use angles. Are you following, right? And then an examiner decides to give you a special angle to be the value of an angle. Or you are dealing with rotational dynamics, circular motion, where you deal with angular displacement. Am I communicating? Now, in such cases, if special angle is given to you, you can evaluate them with that calculator. And of course, you're expected to know all of these. This triangle is going to guide you. Alright guys, now we're going to move on to deal with angular conversion from degree, alright, to radian. And of course, time unit conversion, where we'll express degree in minutes, in second, and of course in hour. Remember, in the unit circle, displaying once again on the screen, you see that angles can be expressed in other units apart from the degree we know. And let me also even remind you this, by the way, in your calculator, you could see some keys where you have something like DMS. That will represent degree, minute, second. You could also have DRG or DGR, right? That represents degree, radian, gradient. These are various units in which angles can be expressed. Like in this unit circle, you see where you have something like 30 degrees, and you have the line represent that 30 degrees, all right, an angular measure from the horizontal, and you see somewhere written pi over 6. That pi over 6 is the radian value of angle, which is given as 30 degrees. So how do we know about all these conversions? For example, if you even have something like 90 degrees, 90 degrees, you can see that the unit circle is pi over 2 radian. So instead of my telling you, okay, evaluate sine 30, I can tell you evaluate sine pi over 6. Alright? So how do we go about that? Think about, maybe you are given 150 degrees and I ask you, how many minutes is equivalent to that 150 degrees? Because that's going to give you 25 minutes. How do we know that it's going to be 25 minutes? All right? Imagine your minute hand turns, and then it's pointing to 25 minutes. How many degrees is that? 150 degrees. Who told us? The next aspect of trigonometry is going to deal with that. So, you wouldn't want to miss that, right? Come along with me as we move on into that angular conversion. Do click on this info link and follow along as I take you on that conversion and calculation.